This is assignment for part 1. As part of this, as part of this demonstration, what we are trying to explain is our code implementation procedure. We'll go through each structure during the code main logic of the code.
So this outlines the method for part 1. And then the second part of this report will outline the observations for part 2 of assignment 4. The part 1 is the dining philosopher's problem, we provide the code separately on the Bitbucket website, and also have a separate video clip that demonstrates the implementation. Here we just outline the method for this we use to solve this problem. The philosophers are identified with LEDs, which show their activity by means of their status, of their state. The LEDs can be in state solid on, which means thinking, or blinking, which means eating, or off, which means waiting for resources. There is an initialization procedure for the LEDs, and then each LED is going to be enacted by appending to a string that ultimately will create a folder that will be used to set the direction and the value of that LED in the system's class GPIO folder. And we also have another procedure that will set the LED state. This is mostly borrowed from the Lab 4.
Slide.
Here we have we showed the structures that are involved in the implementation. We have the structure philosopher declared first, but defined a little bit later. It's declared first, so it can be accessed here. The fork, the resource itself, is a structure with one member, where the member is a pointer to a philosopher that currently owns or uses the fork. Then there is another structure called the fork manager. This is essentially a pair of members, one being a fork structure and another being a mutex variable associated with that resource. Access is a mutex variable here. This will be used to lock and unlock the access to that particular resource. And finally, the philosopher is a structure himself with two members representing in the required order the resources that he needs to acquire before he can start eating. The first one is the one that implements that he needs to grab first. And this is the second one, is the one that he needs to grab second. The order is important in preventing the deadlock. And actually, there is a third member here, the LED that is associated with that philosopher. Here then is the outline of the global variables, which are visible by all threads. Then the random number generator, which is a modification of the standard library from C, the rand function, which is modified in order to generate random numbers uniformly distributed between a minimum and a maximum values. This is in milliseconds. For the implementation itself, we have a procedure for acquiring the fork and a procedure for releasing the fork. Both follow the similar thought process. They have two arguments: a pointer to a fork manager, which again is that pair of fork and its mutex access variable, and as the second argument, a pointer to a philosopher structure, which will emulate the philosopher that currently owns the resource. That when he tries to acquire it. And we can see here that we do this by locking the resource by setting the mutex variable, and then this is just a check, and then we set the pointer to be the second member of the fork. The pointer is set to be the single member in the fork structure. Then this is the release of the fork follows the same reasoning. Then here we see the procedures for thinking and waiting. The thinking essentially is enacted by the argument, which is a pointer to the philosopher who is acting the thinking activity, and essentially for a random amount of time, thinking time, between a minimum and a max. This is drawn every time a philosopher starts another sequence of eating, thinking, waiting, and it is visualized by setting the LED state. This is the waiting. Again, one argument which points to the philosopher structure that is waiting. The LED state is set to 0, and he tries to acquire the fork, which has been locked at this point, and then this is the first fork and this is the second fork. This order is essential in preventing deadlock. And finally, for eating, again, pretty much the same idea, but here we have to define the blink on and off times. And essentially, this next time toggles between blinking on and blinking off, and this is how we count down to the end of the eating period. And finally, this is the procedure, which is the routine invoked when we create a thread, and it essentially calls the think, wait, eat procedures. Finally, the main function provides that the 4 arguments for the minimum and maximum eating and thinking times. And here is where this is how the threads are created. Each thread has a thread ID from a 4-element array. The philosopher structures. This ethers is an array of structures, 4 structures, and the fork manager is an array of 4 fork managers, which in turn are a pair of fork structure, resource, and mutex variable for accessing it.